one thing that makes the identification of forces important is that, so if I do this, okay, and I move this chair, you'll say, okay, Professor Menendez is pushing that second chair. But for physics, that's not true. The pushing of the second chair is done by the first chair. I'm only pushing on this one. So when you try to identify forces, the forces that appear in the equations are the immediate forces. It's not that, yeah, you are pushing on something, it's pushing something else, okay, and then you are legally responsible for that pushing. Yeah, legally maybe, physically not. Okay? Physics is whatever it touches, okay? So if I kill you, okay, just the bullet kills you, okay, not me, okay, I just activated this gun. Okay? Legally, it may be different. Okay, so this country never knows. Okay, so now we have this person here standing. The reason I'm saying all this is because we have this person standing here, okay, and okay, I'm not going to draw the windows here. Okay, draw the seats to or whatever. Okay, so we have this person standing here, and so we're going to analyze the forces exactly the same way we did it. So we just imagine surface there surrounding our object, okay. And where is our object touching the environment, okay? So where my feet are. Okay? So there could be here a normal force. There could be here friction force. And nothing else. That's the only place where it's touching the environment, okay? And then there could be a long range force, okay, which is the weight. Okay? So the only forces that can appear in my free body diagram are the normal force, the friction force, and the weight. Anything else has to be wrong. Switch back to the... So which one do we know to be wrong? 2 and 4. Okay, that thrust force is a force that is applied on the plane, on the wings of the engine actually by the air, okay, that is being expelled by the turbines. Okay, so this is the force that is applied on the plane, but not the force that is applied on me. Of course, that force will allow me to go to arrive wherever I'm flying, but it's not force that is directly applied on me. So it does not appear in my free body diagram. Okay, so we can discard 2 and we can discard 4. So now we can discard 5, okay, because there is no weight there, and we know the weight is there. And so now we have either 1 or 3. Okay? So which one is correct? 1 or 3? Okay. So in order to figure that out, okay, we use our tools. Okay, we have this battery of tools. We have this kit, okay, that allows us to solve all problems without even thinking. Okay, without doing any math and without even thinking. Okay, what is the tool? The tool is the free body diagram and motion diagram. Okay, so I'm going horizontally at constant speed. So here is my motion diagram. What is the acceleration here? 0. Okay? That's the velocity. Okay? Now let's do the motion diagram. Sorry, the free body diagram. So we have the normal force. We have the weight. And suppose we have the friction. So what is the direction of the net force? This will be the net force. Now wait, F net is supposed to be equal to MA. Now we got a problem. because we know this to be true, and we are saying that the net force is to the right here. Okay? And so, what happens then? So what is wrong here?
There's no friction force.
There's no friction force, okay? And you know there cannot be any friction force because you know the force will be zero. If there is any friction force, the net force will never be zero because all the other forces are vertical. Nothing will compensate. So if there is friction, the net force cannot be zero. And you know that the net force has to be zero because you believe in Newton. Okay? And so, now you say, well, how come? They are moving at 800 kilometers an hour, okay? Yeah, but you're not being accelerated. You are moving at that velocity. You want to keep going at that velocity. Nothing, if you want an external action can only change that, but if you are going at 800 kilometers an hour, the world is happy with that, and you are happy with that, and nothing will change. Okay, only if something acts on you will change that. So for constant velocity, you don't need any force. No, I tell you a story. There was one of you, not sitting here, came to see me after this test. Okay, and this student was very agitated. Okay, that guy marked his problem. That he got his problem wrong, and so So started expressing, well, no way, okay, there is no way you cannot have just the same argument that was talking about there. There's no way you can have you can be going so fast, okay, without the force pushing you. Okay? I said, no, you're confusing these. Force is related to accelerations, not to velocity. Your velocity could be huge, but you don't need any force for that. So you need a force to change your velocity, okay? And then, so this student who is doing otherwise doing very well, so he felt quite embarrassed, okay, because he understood that he had made a big mistake. But then he came up, okay, so he was thinking, okay, so 15 minutes later, so he knocks on my door and said, okay, but here it is, okay? There is a problem with you. There is a loophole here, okay, in which my answer could be correct. And so the loophole is the following. So if you read the problem carefully, say, it's flying horizontally at constant speed. And then he said, okay, this could include a case where the plane is flying in a circle horizontally at constant speed. So now you're not moving in a straight line, now you have acceleration, and now you have friction. So he had a point. So next time I use the problem, I'll have to modify that. But I told you, well, I'll give you credit for the problem if you have not embarrassed yourself by arguing the force of acceleration. So I should have, because of that statement, I should have reduced your score by 1 point. Now you came up with these legalese that I give you credit for that, so 1 point, so the net change is 0. So I did not change the score. So you know that, so you can actually, and actually it is a good thing, not for the points, okay, because but it's actually a good thing to try to play this application this way, to try to find possible interpretation under which some other answer might be possible. But that way, you still, if anything, we're physics. So. Okay, now we should be able to tell this one quite easily. Okay, so the spring is compressed. We have a spring that is compressed, the mass is and we have the spring force, and we need to figure out, okay, what is the correct free body diagram for this object. Okay, so which ones can we tell immediately cannot be correct? 2 and 3, okay? Because 2 and 3 there is a net force, and so the object cannot be stationary, okay, there is a net force. So now, the spring is compressed. That means that it will apply force to the mass. Okay? And so if you compress the spring doesn't like to be compressed. So in what direction will the spring be pushing the mass? To the right. Okay? So you know that there is a spring force to the right, so you can discard 1. And in fact, you can discard 5 because 5 has the spring force in the wrong direction. Okay? And then you know that if there is a spring force to the right, something has to compensate it because you know that the net force has to be 0. So you need a force opposite to the spring, and the only force that will do that is the friction. Okay, so you do need friction because you can't balance the 3 forces without friction. Okay. Let's go to the next one. Was it clear now?
So is the answer 1 or 4?
So the correct answer is 4, okay? Because the spring is, you are told that the spring is slightly compressed. Okay, so you know that the 1 cannot be true because if the spring is compressed at all, then there is spring force.
But since it's being canceled out, then you just make back the diagram? Or do you need a...
No. So in the free body diagram, okay, that's a good question. Okay, in the free body diagram, so when you do a free body diagram, you include all the forces. Okay. Now some of these forces may cancel out. You put this. So now when you do F net, this is say F1. F2, F3, and F4. Okay, so you have here 1 plus the other, plus the second, plus the third, plus the fourth. So now this may cancel out, but in the free body diagram, you first include all of them. Okay? So otherwise, the free body diagram for an applet is not moving with just a point, because we know, of course, everything cancels out. Yeah. And so maybe here we have these 2 and 3 may cancel out, and 1 and 2, but you put them. It's very important you put them all. Otherwise, you sort of you can get incorrect answers. And of course, in some cases, okay, although they cancel out, they're not 0. So you may have a problem when you're asked to calculate what is the friction force there, knowing how much thing is compressed, what is the friction force. So you need to calculate that. So this problem could be, let me just see back here. So this could be a problem. This could tell you, variation of this problem will tell you, okay, the spring constant is whatever, K equals something, and the spring is compressed by 10 centimeters. And so what is the friction force? And what you do, so you say, well, if the spring is compressed by 10 centimeters, Kx is the spring force, so that will give me the magnitude of the spring force. Fsp will be K times x. Okay, and then it has to be equal to the friction because of this free body diagram. Okay, so the magnitude has to be the same as the friction force. So that will give you the magnitude of friction force. Okay. So it is important you put them all there. Okay, problem like this.